All right, next I'd like to take a look at ways in which you can move heat from one place to another. We saw in the last video that heat does a number of different things. It can change the temperature, it can change the pressure, you can also change the phase of a substance. But how do you move that heat from one place to another? And so this is associated with the principles of conduction, convection, and radiation. And so what I'd like to do is explain each of these to you as well as I can, and then to try to give a physical example of how it relates to meteorology. Okay, so first we have conduction. And so we can think of that as being the transfer of heat by molecular collisions. So for this example, let's say we have a frying pan, and that frying pan is set to have some kind of a fire down beneath it, and so that the frying pan gets going at a much higher temperature. And then what's going to happen is that the molecules that are inside of the metal are going to start to vibrate more quickly. Okay, and so instead of the molecules moving faster the way they do in a gas, what they do is they vibrate back and forth because they're held in place by the solid structure of the metal that's within these things. And so the heat then moves into the frying pan this way. Some of it cooks your food, but some of it moves out this way to your hand. And so you go, hey, would you mind handing me that frying pan, off the fire? And so you grab it, and guess what? You get burned. Okay? The reason you get burned is because there's a very rapid flow of heat. So one molecule pushes against the next, that pushes against the next, that pushes against the next, and the rate at which these molecules start to speed up in their motion is a rate at which the heat flows. In this case, flows into your hand, burns your hand, you let go of it, drops to the floor, dinner's ruined, race off to the emergency room at the hospital. You treated for third-degree burns, hand gets all bandaged up, and then you come home. And you go, well, I'm kind of hungry, let's cook up some dinner. And so you start this process again, and then your friend says, hey, would you mind grabbing that frying pan off the fire? And you look with your bandaged hand, you go, well, this time I'm going to wrap it up. I'm going to insulate it so that that heat doesn't flow so well through the handle into my hand. But that would be an example of conduction. And so each molecule then delivers the heat energy by hitting the adjacent molecule. And so one molecule hits the next one, that one hits the next one, that one hits the next one. And so they all start vibrating faster, but the rate at which that vibrational chain moves along that path is equal to the rate at which the heat flows. And in some sense, it is very much like the flow of heat is very much in this situation like the flow of water in a tube. So how does this relate then to the Earth? Well, the radiation that comes in from the sun, we'll talk more about how that radiation gets to the Earth later. But let's say that that radiation hits the surface, and then the surface heats up. And so we get this hotter surface that is associated with all of the radiation. So this surface then is hotter, and it's hotter than it was before. But not only that, it's hotter than the air above it. Okay, so here we have the air molecules above this hotter surface. And the temperature of these air molecules is less. So they have a lower temperature here. So basically then, heat is going to flow from high temperature to low temperature, just like with your hand. This is lower temperature. This is higher temperature. So the heat then flows from higher temperature to lower temperature. And the same thing happens here. The hotter surface then collides with the molecules, and each time the molecule collides with the surface, the molecules pick up some extra energy. The result of this then is that the air temperature rises. Well, if the air temperature rises in this region, then that can produce a high pressure region. Because here, the molecules are moving faster. Remember that how fast those molecules are moving has a lot to do with how hard they hit any surface that they run into. And so higher temperature in this case generally means higher pressure. Because now this air has been heated up by coming in contact with the surface that in turn got hot because of the impacting of the surface by solar radiation. The absorption of solar radiation by the surface heats up the surface, and that heat flows from the surface through collisions to the air molecules that are above the surface. So now we have a high pressure region. But maybe nearby things aren't as hot for some reason. Maybe it's in the shade or whatever. And so over here, you have cooler, low pressure air. So a lot of times we'll use blue to represent lower pressure and red for higher pressure. That we learned a couple of videos ago that high pressure air naturally wants to move toward lower pressure air. And so look what's happened then. We've gone from conduction to the second type of heat transfer mechanism, which is called convection. Now in convection, instead of there being molecular collisions, where one molecule bumps against the next one and that one bumps against the next one, and that chain reaction is sent along that way, these molecules say, hey, I don't want to bump into you. I want to take my energy straight there myself. I'm not going to bother with any of this in-between collision stuff. I'm just going straight to the low pressure area myself. And so we can think of convection then as being the transfer of heat by mass motion of molecules. So examples of this would be wind, but also ocean currents would be convection currents. Those would be the main ones that we'd be looking at in this class. And so typically then, in our conduction situation, the collisions only happen within a few inches of the surface. But this gets the heat going And then once that heat goes, then the principal method of energy transfer through meteorologic processes happens through convection. And that's what drives much of our weather, are these wind currents. And so much of meteorology then is associated with convection currents. And so oftentimes we'll have something happening, like for example, say in this next example, we have, instead of just air flowing from high to low, let's imagine that the high and low pressure regions are moving with respect to each other, which can often happen. They can be driven by other larger scale features on the surface. But here's an example then of how different pressure air masses can move. And how they interact with each other. And so we're going to have a relative motion between high and low. It could be the high that moves toward the low, but there's also always an attractive influence. And sometimes it's the high that stays fixed, and it's the low that moves into it. So in this case, let's say that the high pressure region is associated then with warmer air, more pressure, of course, because that's what high means, is high pressure. But we're also saying higher temperature and more moist. Why more moist? Well, because higher temperature air can keep more liquid water in the vapor state, and so can support water molecules that are in the gaseous form. And so in other words, low pressure air tends to be cooler. Of course, lower pressure, by definition, and dry. Now, because it's cooler and lower pressure, it also tends to be more dense. What does this mean? It means that when the high pressure region comes in contact with the low pressure region, the high pressure region is going to tend to float. It's going to go up because it's like a sponge floating on water. And so typically then warmer air tends to be less dense. Remember we talked about density before. That's mass per unit volume. And so lower density air mass means there's less mass per unit volume. Can we understand that? Well, if the molecules are moving around faster, then they are naturally going to tend to have an average distance that's farther apart. And so they tend to capture a larger effective volume. Because of the fact that they're moving faster, they interact with anything that gets in their way and they knock it out of there. So that they've captured more space, essentially, than the lower pressure air. So that makes it less dense. So in this case, let's imagine that the low pressure air mass is moving toward the high. Now, oftentimes this might look like this on a weather map. Where you would have your low pressure air mass moving in toward the high like this. So you can have something that looks like that. And then at the moment that the low pressure region comes in contact with the high, we have what's called a weather front. because along this line we can get rain. Now why does this happen? Well, as the low moves into the high, let's take a look at what's actually happening with the masses. So instead of looking at it from a top view that's kind of symbolic here of this moving low, with a little jagged teeth on it, we'll instead look from a side view. And so here's the high, here's the low. The low is moving toward the high, but now the low starts moving into the high, but look what happens. Because the low has more density, it starts pushing the high up. Okay? And so as this starts to happen then, eventually the low gets directly beneath the high pressure air mass, and that high pressure air mass is forced to higher elevations. So this is the process then. It's far away, then it starts coming in contact. So that's like this situation here, where it's coming in contact with the high. We're starting to get rain along this front. Why? Because as the high pressure air mass rises, it expands. And cools. Now there's two reasons for this cooling. One is that in the troposphere, the higher up you get, the lower the temperature is. And so it's naturally going to tend to get cooler as you get up to lower pressure air, which is what's happening in the upper atmosphere. But the main reason for this, particularly for fast-moving storm fronts, is that the expansion does work, and that work has to come at the expense of the internal energy of the molecules. And so as the high pressure air mass rises, it cools. This causes water, which was in the vapor state, to condense into droplets. And so we start getting more and more of these little water droplets forming, and finally they get big enough to where they're no longer stable. They can't be supported by the cooling energy of the high pressure air mass. The pressure's dropping fast. As it rises, it expands, cools, water condenses into droplets, and we get rain. So essentially then this kind of thing where the low pressure is below and the high pressure is expanding and is above like this is the genesis for a thunderstorm. And the faster the high pressure air mass moves up, the faster it expands, faster it cools, and the more effectively all of the moisture, which was contained in the vapor state within that cloud, starts to dump out. And so this rising effect can continue to happen until we get to the top of the troposphere, which, as we saw before, is the tropopods. So this is at about 10 kilometers height. And so this expanding air mass then is going to keep moving until it experiences some resistance due to the inversion layer of the stratosphere. And so it gets this kind of an anvil-shaped top. So a really unstable thunderstorm that continues to rise usually just rises until it gets to the top of the troposphere, and then it can't go any farther, and so it starts to spread out, producing that anvil-shaped